Oh yeah, so if you haven't already, attendance sheet is up, and you don't have to, but if you want some feedback on your project, it'd be nice to have your project document here and get some peer feedback or like my feedback. Alright, so let's get started. So sequential models. Today we'll be talking about how to deal with data that is sequential and how to build models on top of that. Usually that deals with like NLP, things that deal with time, but I'll get more into the detail on that. So, background. First off, we're going to start off with basic probability, and particularly conditional probability. So, conditional probability is the probability that something happens given some event, another event happened. So, one simple example is what's the probability that you pass given that you studied before, or the probability that you pass given you were gaming before? Well, most people would agree the first one is greater than the second one. But the fundamental idea is that you are given some prior information, and probability this is called a prior, or never mind, that's the wrong thing. But you're given some prior information, and you want to calculate the probability of something happening after it. So what that means is that we can take advantage of data in deep learning systems. So in like a time series or like a bunch of things in sequence, you can take the meaning of what happened before and produce some kind of probability on what would be likely to happen after that. So another important thing to note is conditional independence versus dependence. And this is just the basics, where the conditional independence means you have the probability of x is equal to the probability of x given y. This means that the probability of x does not change depending on whether y happens or doesn't happen. So the probability of x will always happen with some sort of probability. And then dependence is just the opposite, where it's actually different. So instead, this probability could be changed by something else happening, some independent variable y. All right, so now that ties in very well with the definition of sequential data, because what we're essentially looking at is a conditional dependence, right? Our probability of x is not equal to the probability of x given some previous data in a sequence. So this sequence is basically, we have x0, x1, x2, etc. Say you have a bunch of different points on a graph, or like, say a sine wave, right? You would have x1, x2, x3, x4, like that. So because if you want to find out like what's x5, or what's x5 over here, you do need this kind of context to find out what that is, kind of. But otherwise, it's really hard to find the prior probability, the probability that it will happen regardless of anything happening. So it could be, x could be on this whole spectrum here. So we're trying to take advantage of previous data. Does that make sense? So other examples is like in NLP, you want to predict what this word is right here, and you're given information previously. So you can think of each word as one data point. And this data point would have some various values. In NLP, you usually model a single word as a vector, and a vector has multiple attributes of the word, right? So basically, that's what sequential data is, and now we're going to move on to sequential models. So sequential models is basically a way to put on top of the data and say, now I know, like, given this previous data, what is the probability? And it will actually spit out a probability. So it's the same thing, same concept. And we have multiple examples. We have RNNs, LSTMs, and GRUs. We'll go over RNNs and LSTMs, and also GRUs are also a popular framework. Hold on one second. Pizza. Hello? Yeah, coming out. Okay. Devin, could you? Alright. So these are some examples, and then here are some applications like natural language processing, audio signal processing, reinforcement learning. Basically anything that deals with time is a very good use case. Anything that deals with natural structure of sequence. So in language, you have a sequence to the words. In audio as well. So now we'll go into recurrent neural networks and how we do that. So first off, with the basics, we're going to dive into recursive functions. So what we're trying to do is basically we have a sequence of inputs, and we want to generate a sequence of outputs. So that's x and y, right? So for each x, there's a corresponding y. And we say, well, we want to learn some function that takes in all the inputs up to time t, and then spits out a corresponding y for that time t, right? However, there's a problem with this because you would have to design a specific function for any amount of variables. Say t equals to 3, and you have x1, x2, x3. So now you have a function that takes in 3 inputs, and if you want to learn that, you can learn a function that takes in 3 inputs. But what if you want at time t equals 4? Well, now you have another variable, and you can't you can't have this function magically adapt to 4 inputs. So what we want to do is something that has recursiveness. And that's where recursive functions take into play. One second. Hello? Okay, I'm coming out. But so we have this yt equals f of st. And now st is what's called a state. It summarizes all the information necessary in order to predict yt. So what is that information? Well, that's what we have another function learn for us so that we can use that function to predict yt. So we take x to x1 to xt, put it through something, it spits out a state. We take the state, put it into another function, and it produces our output. Okay. So this is the definition of that function. So we have one state, and then it takes in a previous state and some parameters that we learn, and it outputs the next state. And you can see it's sequential, where if this is t minus 1, we apply that function, and then we get s of t, we apply it again, and then we get st plus 1. So it's keeping track of state over time. All right. So here's a new thing. We want to include, before we just dealt with states over time, but now we want to include additional information. So we add an input x here. So now instead we have a function that takes in two things, two parameters, so that would be your hidden state and then your input. And then of course there's the learnable parameters that are on the side. Those are theta. But essentially what you do is you have something that recurses, and this is called folding, or you take this and put it into here, that's folding, and then unfolding is going the opposite way. You take a recursive function and then you lay out step by step what would happen if you expand it over the number of time steps. So what is this black box here? That is f, because you take in h, this state, and then x, put it through the function, and then you get the next one. Is that clear? What?
Beginners who understands what this diagram is like, obviously abstracting to know that works. 1 through 5. 4s through 4s.
I think.
Okay, so I have a question then. So
Yeah, go ahead.
The h is a state, and
Yeah.
then x is input to
Mhm.
the function f, and then it uses a state from the previous state, which is like
Yeah.
h, and then you
So if you want to write it out, you can say h of t equals f of ht minus 1, comma, xt.
So what will end up happening is basically H, you can kind of think of it as memory within the cell, which we'll get into more in the slides for this.
All right. So we have some goals of predicting in our neural network. So we want three things. We want to summarize. This is basically summarizing all of the previous data so that we have one single state, as we talked about. We have our second goal, which is predicting. We want to predict the actual value of y. And then our third thing is training. So we want to have some way to learn our parameters. So if we dive into detail, we can say our network should take a previous hidden state, h of t minus 1, add a new input, and then get the current state, ht. This is what I said before in the previous slide. And then, so this ht now is their new hidden state that summarizes, right? And then using that h of t, we now predict ot, which is our output. And this is also known as y hat. So this predicts the real value of yt. So the goal is to get ot equals to yt. And then our training is we just compare the output ot and then yt, and then we get some error and generate a loss here. And then we use that to train our neural network with backpropagation, which we've done with all our previous architectures that we covered. So we're gonna show this in a diagram, so don't worry if you don't get everything. So here's a basic RNN cell, right? It's pretty simple. We have our x, and we multiply it by u. This is a matrix, a weight matrix. That's learnable. So u, w, and v are learnable parameters, or also known as theta. And basically we get from x to h. So basically what h is the weighted sum of x times u plus w times h of t minus 1, right? It's the previous step. And then actually we'll show this unrolled so it's more clear. So as you can see, when we want to get h of t, we take in two inputs. We have h of t minus 1 times w. We have x of t times u. And then when we sum them up, we get this. Minor detail is the activation function, which we'll go over later. And then we have that. If we want to get the output, we just do that times that with that, or that times that. So you can see you have a graph that builds up over time, basically.
So how are the outputs I guess kept track of? Because you're trying to get towards y axis, right?
Mm-hmm.
So I guess run the graph, does the output get passed along to the next state?
No. So only the hidden state gets passed along because we want our hidden state to keep track of everything in the past. So once we get a hidden state, we know that we summarized everything that happened, and then we can use that to produce a prediction.
So I guess my question is, how do you know if you're making progress towards the correct conclusion?
So we would only know that with our loss function, basically.
So you can imagine these letters, like the O, let's say the words, putting many different words trying to make a sentence. So let's say sentence is just completely wrong. Sentence will have some classification, so you just do essentially just find the difference between that and what it's actually supposed to be, not the error that way. So yeah, so it depends on the problem as well, because there's different types of problems. So this one has maybe
Yep. So to make this more clear, we'll see the bigger picture now. So basically, once we get an output, we can now use that to compare to our target and our target y. And from there, we generate our loss for each step. So this is our error that we can use to keep track of how good or bad our network is, and then do backpropagation to train the weights. So any questions? Again? All right. Well, we'll go back to this graph when I explain backpropagation. So here's the basic equations. So initially, we have our find function, and we use that to get our hidden state. So what I told you is we have the hidden state times the weight, the input times the weight, and then we add a bias and to get a find function, and we pass that affine function to an activation function to get the hidden state. So back here, essentially what that equation is saying is we take, say, this one times a weight, this one times a weight, and then we add a bias. We get A, but we're not done in this graph. We have A and we didn't put it through an activation function to get H here. So that's the first part. And then once we have H, we theoretically know all the information necessary to predict what O is, the output, or the prediction. So we take H multiplied times V and add C. It's just weights times plus a bias. And we get our output. All right, so, and that in the graph corresponds to getting weight, the hidden state, times V plus C equals O. All right. And then once we get O, if we're doing classification, we can use our softmax function, because softmax is used for classification when you have multiple classes. So by doing this, we will get a bunch of prediction probabilities ranging from 0 to 1, and that's the prediction That's the likelihood of it being a single class. And then here's the loss function. And you can also put in like any other loss function depending on what your task is. If you're predicting actual raw values, like say you want stock market data and you have a bunch of previous prices and you want to predict a future price, then you wouldn't use softmax in this case. You would use something else, because softmax produces values between 0 and 1, which you don't want. So now once you get the loss, we want to train it, right? So this is called backpropagation through time. Because the thing about it is, we're not just doing training a regular neural network. We're training a neural network in 2 dimensions. One going back to the input, but one going back to the left on previous time steps. So if we look at this here, so we had our loss here. To find the derivative with respect to the loss, we'd have to compute the derivative with respect to O, and then from that respect to HT, and then from there we can calculate the derivative with respect to W and U, which we can then use to train. And similarly for V. But the thing is, you can't stop at one step. You have to do multiple time steps. So you have to take the derivative from W to here, from here to the next W, and etc. So you have to go through backwards through time. And you do that for how many steps you did to get the output that you desired. So if it was at time step 4, then you would have to go back 4 time steps. And one problem with this is that you have the vanishing gradient problem, which we discussed in a previous lecture. But basically, if you multiply by a weight that's smaller than 1 multiple times, then you get much more smaller gradients, because it has much more or less influence to change the weight. All right, so here's some types of problems that you can use RNNs to solve. So one-to-one, it's actually, you don't even need a neural network, recurrent neural network. And this is just like literally the same thing as regular classification, or just using a feed-forward neural network, but instead going from bottom to top. And one-to-many, in this case, you're going to start using a neural network, because you have one input, but you want to generate a bunch of things. Say you have like an image, and then you want to say what's a natural language description of this image. So then your description is sequential, because you have a bunch of words. And then you have many-to-one. Say like you're given a video. A video has a bunch of frames, so that's a bunch of time steps. And then you want to compress it into one classification, say the genre of the video. Or you want to predict the sentiment of a sentence. Say you have, you are bad. And then it goes through the network, takes each input into a state, and then aggregates the states until it has one final state. And then you use the state to predict the sentiment, which would probably be 0 or something. And then you have many-to-many. There's multiple ways to order this, but it depends on what your problem is. Say you're given a video and you want to predict a label for each frame. Now I want to ask you, which of these 2 do you think is the correct answer? The first one or the second one? Yep, the second one. Why? Because at each step you have a corresponding label. So, and at the next step, you have also a corresponding label. So it's basically, it should be this kind of architecture. Because there's no need for you to know what's in the future, say at this step. You don't need to know what is time step 3 in order to label what time step 1 is. But that's different in the case of, say, you want to translate a sentence. Why would you want to know everything beforehand and then translate it? Well, because in language, say, you don't really, like sometimes different languages have different order of words, and so like you need to know the full context of the sentence in order to translate it so you can produce the correct ordering in a different order in a different language. So that's why you have like this one point where once it summarizes everything beforehand and then finally spits out a sequence output. So also other variations to RNNs I'm going to briefly discuss. So we didn't talk about deep RNNs, but there's a small problem with it. Because first of all, we had the vanishing gradient problems because we had larger time steps. And second of all, well, it's mainly just adding deeper networks would not solve the inherent problem of the deep time scales. Because think of audio, for example. A 1 second audio clip has so many data points in between. Like, an MP3 file is like, it has 48,000 hertz or something. Yeah. So that's a lot of information and a lot of time steps. So what we need to do really is, like, the current research is mostly working towards figuring out how do we effectively aggregate this data and then produce stuff where there might be maybe millions of time scale steps. And then, and some solutions to that is using like convolutions, attention, and also we're going to talk later about a term called gates, and like passing information through longer time scales. But that's for LSTMs, which we're going to talk next. But a quick intuition on why you would use convolutions or attention. Convolutions, basically you have a sliding window. So you have a fixed amount of information it's looking at. So it would be faster in that way. So you don't have to look back so far. If there's, say in audio, you have a wave, sine wave, you only need to look at like a certain portion of the sine wave to determine what's next. You don't need to look at the whole history. And it's also just much more faster. So, yeah.
When you say making a deep, what do you mean by that?
So, like in deep neural networks, you would just have much more layers. Like, say this is like one layer, but say you had layers on top of this until you got to some output instead. And then similarly for at the bottom, you could have more layers going until you had summarize to a hidden state.
So if that wasn't clear, this is like one vanilla RNN cell, so you can stack them on top of each other. So like that always going to be the X for the next cell.
Also, I want to clarify, well, it's okay to make them deep. It's fine. Because like if you have like a big multi-dimensional image, for example, that's like that's a huge vector if you flatten it. So you want to get that into a manageable state. So you want to compress the input into something smaller. So like a video into 128 dimensional vector of a hidden state. So that's when you would use more deeper network. This, instead of one function of you would have a feed-forward neural network smashed in between there. And then you could similarly do that for W and V as you seem necessary. All right, so next up we'll be going over LSTMs. You can ask me any questions. I think we'll take a 5-minute break for pizza.
just take 132 out at any point.
Yeah.
It's unbelievably as in.
So, really?
I think the math version generally is better.
CS version's not
I like 131.
We can just teach it.
Hmm?
Did you like I think it depends on the teacher. Like I had it with auto.
I bet it is.
Okay. It's up to you. Just so that you can get the math version.
Well, if you said so, I would be cautious. And also, Riddles suggested me to take 237 next semester instead of one. So I asked her which one should I take. 237.
You can take either one or 237 will enable you to take more probably statistics. That's going to help more if I'm a class like 350.
Yeah, that's her reasoning.
Yeah.
I agree with that in that sense. But yeah, 132 will help you with like more algorithms class or like with algorithms like 330 or like upper level classes like 540 like quite interesting.
I see. But you would still recommend taking math? Yeah.
I can't speak for the math version, but I know my experience in the CS version was not the best. Yeah. I remember learning, drilling into my head in the last weeks before the final, like what eigenvectors were. It's like
Yeah. they don't really stress that as much as they probably
yeah,
should.
and then the rest of it kind of just went over my head.
I see.
My advice, I would keep asking around what people thought of the course. But I've heard good things about the math version.
So, math version is
I'm sorry,
it's like a 200 level class,
Yeah, it's like two.
I'm sorry, 735.
I forget the actual number.
but 200 level.
Yeah.
I see. Thank you.
Yeah.
Alright, what's up guys? Show of hands, who here has heard of an LSTM cell? Just so I... Cool. Alright. So yeah, basically LSTM cells are just an alternative towards vanilla RNN cells as we saw previously, and they help us solve two major problems, vanishing gradient problem, and in general they're just more robust. They bring the concept of having gates in, which I'm going to explain in a bit. But yeah, so in traditional RNN cells we have just this H node pretty much, and this hidden state is like the only state we have. So it tends to not do too well when we have longer term memory because I would just forget things. So to compensate with that, we're going to introduce LSTM cells. They're going to have two different types of states. We're going to have like hidden states and cell states. So the cell state is essentially going to hold longer term information. It's going to be able to write to the cell state, erase stuff, scale things from inputs, yada yada. All right, so this is what an LSTM looks like. If you guys ever like look up like LSTM cells, you'll find lots of different depictions. This is like just the top one right off Google. So this is composed into 4 different gates. These two being pretty much the same one. So we're going to have a forget gate, an output gate, and I'll just call these two like the input activation gate. So show of hands, once again, who remembers the difference between sigmoids and 10H functions? Who does not know that? Okay, so 10H is going to be a function that maps your inputs between -1 and 1. So if I just go into Google real quick and type in like 10H, you'll notice that your inputs can be either negative or positive. So we're going to be using that for scaling things because sometimes we might want negative inputs, other times we might want positive. Sigmoid, on the other hand, is simply going to scale things between 0 and 1. So if I look up a sigmoid function, you'll notice this is going to be between 0 and 1. And the reason why we use sigmoids is if we just want to see, okay, how strong is this signal? How much do we want to use this? Do we just not want to use it? Whereas 10H is literally just kind of normalizing, let's just make these features smaller or bigger somewhere. It has to be able to be negative. So, yeah, each one of these layers are going to have their own weights. So, whereas in the vanilla RNN cell, you guys might remember we had like U, W, and V. These might just be called WF, WI, WO, or something. We're going to have all these yellow nodes are going to be point-wise operations or element-wise. So, for example, right here, you might think of this as kind of masking over stuff.
I don't know how many concept majors we have, but like if you guys took 210, you probably went over the concept of masking, so maybe that sounds familiar. And yeah, we also have cell states and hidden states. Once again, cell state is going to be longer term memory, and a hidden state is going to be just kind of hidden from before, also works as an output. So I'm just going to break up the different gates we have here. So this is just another depiction. You can stack LSTM cells. So the cell state will continue onwards, and the hidden state is the only observable thing you get. So your output's going to be looking at this more or less. So I covered that. So the forget gate. The very first sigmoid function, what it's going to do is first, when these two arrows combine, that's just stacking the inputs. So you can think of it as like we just have our hidden state, and then we just concatenate with like our inputs. So it's going to be a longer array. We're going to squash that concatenated array between 0 and 1. So this, you can kind of think of it as just forgetting, like, do we really need this input? So if we don't, it's just going to be 0. If we want it, it's going to be 1. And after we squash that, we're going to element-wise multiply it by our cell state. So this is just, once again, saying, okay, what inputs do we not care about anymore, or what do we want to forget? So afterwards, we're going to have the input gate. This is going to be comprised of 2 different weight matrices. Sometimes people tend to distinguish between them as one being input activation, one being input gate. I've heard some people call it gate. That doesn't make sense to me, so I'm going to just call these like the same thing. So what this is going to do is similar to the forget gate. We're going to see, okay, which inputs do we want, and then we're going to scale it. So we'll scale it between -1 and 1 using tanh, and then we're going to just multiply them together. So we're going to see which inputs did we actually want. We're just going to have those inputs scaled, and then we just add that onto our existing cell state. And the last gate we're going to call the output gate. So an output gate is simply going to say, okay, we're going to take our cell state, we're going to scale it one more time, and then we're just going to see which parts of that cell state do we want to release into the hidden, into our hidden state afterwards. So some benefits of having, okay, just high level intuition of like the different gates. Does everyone get the difference between what the forget gate does, input gate, output gate? We good? Yeah, I see nods. Any no's? No. All right, cool. So yeah, when you end up backpropping through this, you'll notice that this addition right here enables you to pretty much like choose when you want to forget like inputs versus not. And the forget gate has a notion of like an ever-changing weight matrix. So you'll notice when we backpropped in the RNN cell, we had like the same W matrix throughout. So that can have, like if that's small, the gradients, then that will cause vanishing gradients. Whereas if we have a changing matrix, then we don't necessarily have that. But yeah, this in general is just more robust. They don't we still have vanishing gradients, but it tries to alleviate that more, and the cell state in general acts as a longer term memory solution. Alternatively, we also have GRUs, which instead of having the 3 gates we had before, they just have 2 gates, reset gates, and update gates. GRUs tend to be more successful in modern times. But yeah, so in PyTorch, in order to use these cells, you would just use torch.nn.lstm. You guys can look at the documentation on how that works. So that was our very high level just rundown of LSTMs. If you guys have more questions on that, look at the video. It's kind of hard to digest like your first time looking at it. But yeah, at this point, of course, we're going to go back into projects. So just so SE board people know, at show of hands, who here has data for their project? So data means you're solid, pretty much. Okay. Who here has an idea of where to get data for their projects? Okay. Who here does not know where to get data for their projects? That's fine. Okay. Who here is not sure if they want to pursue who here might have like a couple projects they want to do, haven't chosen one, or just like foggy on that? Okay. So it's good consensus. So yeah, if you're still like unsure of which projects to work on, definitely try to settle that by this week. Because the biggest problem of neural net machine learning tends to be finding data. So you can have like lots of interesting projects, but like let's say I want to classify different types of airplanes. Where am I going to find an organized airplane, data set from? So that tends to be like the biggest problem for that. So try and iron those details out. And yeah, Devin, do you have any other remarks or?
Yeah, I was just show of hands. I was wondering. So looking forward, we have something like 4 class times left, 4 or 5.
Yep.
So we want to make sure that these projects go and people are making progress. Who here would think that they would benefit from having coming to a little office hours type thing where everyone's just sitting there an hour, 2 hours, come whenever.
Okay.
What are you saying? And just give guidance, answer specific questions. Okay, I think we'll set those up then. Look for something on Piazza talking about that. Also, does everyone have their document describing their project on that Piazza post? Anyone not or have no idea what I'm talking about right now? Okay. Do you know what it is? Okay, so there's a post on Piazza.
Yeah, sure.
Yeah, just refresh for everyone. Post on Piazza here.
Is this only
No.
Okay.
Asking for
my fault.
just a document that's going to have project title and then a paragraph description of what you want to do. So at some point we'll go through all these, make sure everyone seems to be on a decent track. If something looks definitely gonna be able to get done, a lot more details in here, just keeping it realistic for the time we have. Then we'll have a conversation around each of these documents. So yeah, so just make sure everyone's on track, getting things done. Have one of these documents posted on PS.
Yes, just to reiterate, project's going to be due December 11th. You're going to be presenting in class. You might have Kate Singo come in, look at the project, so that might be cool. So
yeah,
you guys,
you want to come check them out.
guys got a little over a month and a half, so I think that's a good amount of time. Assuming we pace ourselves. Depending on how ambitious the project goes, training may or may not be time consuming. If it is, keep that in mind, because training takes time. And yeah, this is the sheet. Would anyone like to, ask questions about the projects right now while we have the fully board attention, or?
Is anyone looking for a team or along those lines?
Good. All right.
If you want to leave now. Oh no, I wouldn't. If anyone is doing a beginner to machine learning kind of project, would love to jump on that. Yeah.
All right. Cool.
Feel free to leave. Hard work anyway. We'll see that.
Resumes.
Love our resumes. Let's do an office hours right now.
Yeah, so
Otherwise I can leave.
we'll be here today once the groundwork and stuff.
All right. Cool.
Yeah.
I'm gonna turn the OBS
So,
off.
like a casual.
Yeah, I'll